To review what we did on part one, we looked at the solar cycle. We understood that ultraviolet radiation creates the ionosphere. We know there's a solar wind that's emitting particles out into space towards us and everywhere else. We know the sun gets stormy. You have these solar flares, the explosions on the sun that emit all sorts of particles and energy. Coronal mass ejections are big explosions where a large mass is blown off the surface of the sun. Normally it doesn't impact us, but sometimes if it's aimed at us, that's fairly serious. And coronal holes, which are open magnetic lines from the sun's magnetic field that funnel particles more directly towards wherever the open lines go, and if it's towards Earth, that causes problems too. So that was the sun. So today we're going to talk about the Earth, more specifically the ionosphere, ionospheric storms, which are a result of these activities on the sun that we've talked about, and the solar indices, which are parameters that allow us to judge what the condition of the ionosphere and propagation will be. So we'll get right into it. I'm going to start with the ionosphere. It's the ultraviolet radiation from the sun, same thing that gives us sunburn, but it's a lot more violent up above the atmosphere. Fortunately, the atmosphere shields us from the worst of it, but the upper atmosphere gets ionized as a result of that. Ionization, in case you're not familiar with it, is where, say, an oxygen or a nitrogen atom, which is what the atmosphere is composed of, it's rarefied up high, but the energy from the ultraviolet will cause an electron or two to be ejected from the atom. Just the energy of the radiation will do that. And so during the daytime, you're going to get a layer of free electrons in the rarefied atmosphere, anywhere from about 50 to 400 kilometers up. And that layer of free electrons is what we call the ionosphere. So this happens in the daytime. You get electron production, meaning that the radiation is producing ions all over the place, free electrons. The ionosphere gets charged up. But then at nighttime, those electrons find their way back to the donor atom of oxygen or nitrogen, and you get recombination going on, and the ionosphere is somewhat deionized. It doesn't go to zero, not all of it. And it's a daily cycle. Every day gets charged up, then it discharges. So that's the first variable. You know, propagation isn't the same 24 hours a day, not by a long shot. Now here's a profile of the ionosphere. If we go up 700 kilometers or more, there's not much air up there. It's really rarefied. And you've got the ultraviolet radiation coming down on top of the rarefied air, and so you're going to get electrons production. Okay? There's not going to be a lot of electrons because there's not much air. But as you come further down into the atmosphere, the production of electrons increases. This is the electron density, electrons per cubic meter or cubic kilometer, I'm not sure what it is. But the production of electrons increases as the ultraviolet radiation comes down. There's more air for it to be ionized. And you get this first great bump here. This is kind of the point where you're going to get maximum production of electrons, and the ionosphere is, you might say, its strongest. It's called the F layer. There's actually two layers. This doesn't show it, but there's an F1 and an F2 layer, two little bumps. Nevertheless, there's the F layer, which is most important. But as you come further down, the ultraviolet radiation starts to fall off because most of it's being absorbed up here. And so it decreases, but it doesn't decrease on a nice, smooth line there. It has these curvies in it. Call them curvies. And they tend to be a bit distinctive. There's an E layer underneath which shows another maximum, and I think that's related to the energy in the ultraviolet. It's going to take more energy to get down to this layer, and so this layer is being influenced by more energetic ultraviolet. But it's still decreasing all the way down. And finally you get to something called the D layer, which is very low. It's about 50 kilometers up. So that is what the ionosphere looks like from an electron density or electron content. So the ionospheric layers, as we've just seen, were the F layers, the E layers, and the D layers. The characteristics vary considerably. The D layer being the lowest one, which is right down at the bottom here, it doesn't do us any good at all. The density of the air is so great, and the ionization that is there tends to make this an absorptive layer. For low frequencies, you can't get through it. And you've all experienced it because, is there anybody who hasn't listened to the AM broadcast band? That's a distinct possibility these days. Okay. You know that during the daytime, you only hear the local stations. And at nighttime, you can hear them all over North America if you want to spend the time listening. And the reason for that is that during the daytime, the D layer absorbs all that low frequency signal. So it doesn't propagate anywhere except locally. At night, we find that the D layer actually disappears. It recombines, and there is no D layer. And so there is no absorption, which means that even at the lower frequencies, they will be refracted off the E layer, and so we hear distant stations. So we're not much interested in the D layer. It's just, from our perspective, a bother. Now the E layer, which is the next one up, is useful. It's not quite so high, but it's good for short skip. You can see here we have a signal going up and coming down. That's what you'd call a short skip, because the distance between here and here, which would be the receiving station, is a lot shorter than, say, this station, which is refracting a signal off the F layer, and it's a longer skip coming down a further distance away. Now this is what we like in HF radio, is to get long skips. But you can get good skips off the E layer, and you can get multiple skips, of course. That's really important. When the sky wave comes back down to the Earth, it is reflected back up, and then it's refracted back down, and you get your long-distance multi-hop communication. But the F layer is the one we really, really want to depend on. It's highly refractive, gives us long skip, and for worldwide communications, it's the layer you want. Yes?
So if I have a pass that goes over water, the reflection of the water going back up is much better than over land, is it?
Yeah, the point was this, the skip, comes off your antenna, goes up into the F layer, we'll say, back down. If it comes down on the Earth, there is a loss in the Earth, a much greater loss than the surface of the salt water. So you're going to get a much lower loss on the reflection from the water than from the reflection on the Earth. Yes. So a path over water is always better. But we don't always have that choice, Could be over a lot of other things that aren't good at all. Okay. Daytime, nighttime. Obviously, the ionization decreases at night because the sun's gone away. The D layer deionizes very quickly. As the sun goes down, the D layer disappears. The F1 and the F2 layers combine to just the F layer because the lack of ionization going on from the sun, it just becomes one layer. These profiles will change depending on all sorts of factors, but they will change. The heights of the layers will vary somewhat. They all have an effect on propagation, of course, which is another variable in terms of HF propagation. This is the same sort of graph that shows the profile, F2, F1, the E, and the D during the daytime when ionization is active. And at nighttime, the density is less. You can see this curve has moved over this way, which means the electron density is less. The F2, F1 just become the F region. The E region is sort of still there, and the D region is gone. There's a thing called the muff and the luff, maximum usable frequency and lowest usable frequency. I like to think of the ionosphere as a propagation window. You've got a maximum usable frequency at the high frequency end of the spectrum, and you've got the lowest usable frequency at the low end of the spectrum. And in between the LUF and the MUF, you've got a region of frequencies which can be used for HF propagation. The MUF is, I guess, limited by the fact that the ionosphere cannot refract back frequencies above a certain high value, like a 30 megahertz signal may or may not get refracted by the ionosphere has to take that signal, and I'll show you a bit more about this in a minute, and bend it back down to Earth. But if it's coming in at a high angle, at a high frequency, it can't be bent back enough, and it just escapes to space. So the upper end is determined by the degree of ionization, the frequency, and the angle of attack onto the ionosphere. So that's the MUF. The LUF is this D-layer absorption thing. We're stuck with that. Our HF signals are able to penetrate the D layer because the wavelength at HF is much shorter than the wavelength at say, broadcast band. Now, it doesn't mean to say that all signals penetrate the D layer, because at 160 meters during the day, 80 meters during the day, we're talking 1.5 megs, 3 megahertz, and so on. The D layer is absorbing just about everything, and those bands are very quiet, if not completely dead. And even 40 meters is affected that way. But things like 20 meters, 15 meters, 10 meters, even 6 meters being the high frequencies, they can penetrate the D layer because of their shorter wavelength, and they are useful during the day. So this MUF and the LF window move up and down in the day. They move down in the day, they go back up at noon, and so on and so forth. So that puts the boundaries on what can propagate in terms of frequency. Are we okay so far? Yeah, all right, okay. Okay, so the propagation, our signals, the electromagnetic radiation, is going to go up, and it's going to enter the ionosphere. And so what happens there? I mean, does the wave just stop? Is it absorbed? It can be absorbed. But how does it propagate within the ionosphere, where you got all these electrons just hanging around? And the answer is that the electric field interacts with the electrons. And because it's an AC field, RF, the interaction with the electron causes the electron, and I use the word vibrate just to keep it simple, but it vibrates in sympathy with the frequency of the wave. And that means that the electron is accelerating, it's going this way, that way, this way, that way, in response to the RF frequency. If you have a an accelerating electron, it radiates. You accelerate an electron, you get radiation. So the energy, you can think of it as passing from the electromagnetic wave to the electrons, where it's absorbed, and the electrons re-radiate it. And by repeating that process, the signal passes into the ionosphere without much attenuation whatsoever. Well, okay, so it goes up into the ionosphere. Then what? Where does it go? It has to be sent back to us to be of any use to our hobby. And the answer is it's refracted. We commonly use the word reflected from the ionosphere. That's quite wrong. It's not reflected from the ionosphere. Reflection is just like we said about Earth. The signal comes down and it is reflected off a conductive surface, being the Earth. It's like looking in a mirror. That's a reflection. But if you put a stick into a glass of water, you'll see the stick goes into the glass of water, and the glass is transparent, and you see the stick is bent at the interface between the atmosphere and the water. You can see it's bent. And that's because the index of refraction of air is different than the index of refraction of the water. So in an electromagnetic wave, like light or RF, moves from one medium to another, it gets bent. Okay? So we could say, okay, here goes our electromagnetic wave up into the ionosphere, and it hits the ionosphere, and it gets bent. That doesn't help much because it's still going up. So there's more to it than just that. And this is what's the amazing part of, I think, of the ionosphere. You have to look where this red line is. That's a gradient. In other words, as you go higher in altitude, the electron density increases. which means the index of refraction is increasing, which means as the wave goes up and it encounters a higher index of refraction along its way, it gets bent just like the stick in the water got bent, only it's a continuous bending process. And it gets bent enough to come back out again. So it's refraction that makes that work, and it's the gradient that makes it work. If it was just a flat line, this whole hobby would be a dud, at least HF would. So this is what's going on up there. The wave is being refracted back down to Earth. When it comes back down to Earth, it can be reflected because you don't have the gradient there. It's just a reflective surface. So I made a note here that the higher the operating frequency, the greater the electron density has to be refracted. And that's another part of the maximum operating, the MUF frequency. At solar minimums, the reduced ultraviolet does not produce sufficient electron density, and so the HF bands start to get poor when we get into the solar minimum because we're not getting the level of ionization we need to get that refraction going. It still refracts, but lower frequencies. Does that make sense? I give you an idea what's going on up there? Okay. I put this little graph in here because it's kind of interesting. This is a measurement of the ionosphere. These are stations positioned around the Earth that send a signal, say starting at 1 megahertz straight up, and see if it comes back. So that's what's happened here around 1 megahertz, 2 megahertz. This is the reflection with a signal going straight up and coming straight down. You increase the frequency, and you see, oh yeah, it happens now about 3 megahertz. Something happens here. It doesn't come back. What's happening is the ionosphere is having trouble returning the signal because you got to remember it's going straight up. It has to turn through 180 degrees and come straight back down again because you're listening. You send it up and you listen to hear what comes back straight down, not at an angle, straight down. So this plots the frequency versus the return. So you go a little higher and you find, oh, higher up in the air, you're getting a signal back again. Well, this would be your E layer, or no, that's probably the F1 layer. That would be the F1 layer. So you've passed the E layer here, which is giving you your first return. Remember, the D layer doesn't do anything; it just absorbs. So now you're looking at the F1 layer, and you can see that it's returning signals down to about 4.5 megahertz. And then at about 5 megahertz, the F2 layer picks it up. But beyond much beyond 5 megahertz, it doesn't come back. This is a measurement of how well the ionosphere can return a signal with respect to frequency. If there's a great degree of ionization, this graph would look more optimistic, say at solar maximum. At solar minimum, it probably looks pretty pessimistic. Now, of course, we don't transmit our signal straight up. That's a waste of time unless you're interested to very close communication, like on HF. If you want to talk from Vancouver to Victoria, the radiation's going up like that with what they call an NVIS antenna, near vertical incident type of antenna, and it comes right back down again. And so under some conditions, you can talk Vancouver to Victoria on HF if you've got NVIS antennas and propagation. So it has important features in that respect. Anyhow, these are measured all day, every day, many stations. You can look them up on the web and see what's going on in terms of how refractive, I should say, the ionosphere is. Okay, so that's a direct measurement of the ionosphere, but there's other things that affect the ionosphere as well: Earth's magnetic field and, of course, the solar flux. So we're going to talk about the disturbed ionosphere. It undergoes constant change by the minute, by the hour, daily, seasonal, and yearly. Take your pick. Hard to know what's going on at any moment. Some of this stuff is predictable. We know that it varies by the minute just because the flux from the sun is not necessarily absolutely constant, so there's going to be little changes there. Hourly, though, I mean, at dawn, the sun is just rising, starting to ionize the ionosphere. At noon, it's probably producing maximum electrons. Back towards dusk, production is falling off. So that's predictable. Daily to nighttime, there's the ionization versus the recombination or deionization. That's predictable. Seasonal, well, in summertime, of course, we have longer hours. The Earth tilted up here in the northern hemisphere towards the sun. It's more intense. That's good. Not necessarily, though. And in winter, of course, we don't get as many hours of sun, and we're looking a little bit more away from the sun. So, yeah, these are just predictable facts, and yearly we got the 11-year cycle. So this is what we can predict more or less, but this is what gets us, is the solar storms, that we talked about last session. You get pretty much unpredictable events on the surface of the sun that cause all sorts of havoc to the ionosphere. It's absolutely related. And so we get these unpredictable eruptions called sudden, sudden, oh my God. Yeah, that's the one, thank you, which we weren't expecting. You can get over-ionization of the ionosphere, which becomes absorptive. And there goes our openings, So you could say, oh, what a bother. You could also say, well, this is all part of the fun. It depends on your definition of fun. Sometimes it's downright frustrating. But being that it's variable, it's like going fishing, I figure. You don't know if you're going to catch a fish or not. Sometimes you're lucky and conditions are good, and sometimes they aren't. But you still go fishing, I guess. Well, it gets worse with the ionospheric storms. We call the ionospheric storm a disturbance in the ionosphere driven by the weather on the sun. The terms that we're looking at here, stormy, brings back the notion of space weather. Okay, we talk about space weather because we have storms and disturbances. Particularly around solar maximum when things are most active on the sun, and that's when the ionosphere is most disturbed most often. So the things that might happen are the signals suddenly become weak, or they're not there, they're absorbed. You get erratic fading, you get multipath distortions, unusual modulations, noises of hisses, obliterates the band noise goes up, and so on. And often it's severe enough that signals you were listening to aren't there within an hour. They're gone. You get these openings just because the path between you and some distance place on the Earth happens to have the right ionospheric conditions for a multipath hop, which means all these factors that are changing have all come together over at least a path, some path somewhere, and you'll hear a distant station that you may have not heard before. Types of storms. So the Earth storms result from stormy sun. There actually are classifications of the different types of storms because they're caused by different effects emanating from the sun. We're going to look at the magnetospheric storm. We're going to look at geomagnetic storms, which are caused by the solar wind. So is this, actually. We're going to look at X-ray bursts, which cause blackouts. High-energy protons in the solar wind result in radiation storms. These are different phenomena that they've classified in terms of understanding what's going on up there. You can say, oh yes, we're having a geomagnetic storm. And if you hear that, then you know that propagation is probably going to be lousy. In fact, if you hear of any one of those, you think propagation is probably going to be lousy. In some cases, it can be an enhancement. Because these things tend to have too much ionization and become absorptive and disruptive, sometimes if it's just the right amount of ionization, your MUFs go way up. And you don't suffer the downside of absorptions and so on. And the MUFs mean, oh, gee whiz, we got openings on 10 meters and we've got openings maybe on 6 meters that you don't normally hear because the MUF has climbed up to 50 or 60 megahertz just for a while. Just because there's been a storm that has been to our benefit. But generally, it doesn't work all the time like that, unfortunately. Okay, sort of. Okay. It's kind of a lot to absorb, I know. Just get the feel for it, and you can watch this again. So I'm going to talk about the Earth's magnetic field, which is ideally looks like this. It's just a magnet. There you go. It's called the magnetosphere because the Earth is surrounded by its own magnetic field, which is really, really fortunate because being a magnetic field, it basically deflects what I would call very harmful particle and ionizing radiation. It's a good thing the ionosphere is up there as well as the ozone because it's absorbing all the high energy particles and radiation so that it doesn't get down to Earth where it would be serious for us. We probably wouldn't even be here. So those types of radiations are looked after up there, thankfully. And it's because of the magnetic field. If the magnetic field wasn't there and the atmosphere isn't as good as it was, we'd be toast. So this is a picture of the magnetosphere. There's little Earth in there. These are the magnetic field lines, which you'll see are very distorted from that ideal picture you just saw. They're squished on the front because here comes the solar wind, and it's pushing against the magnetic field, compressing it. And there's a flow of the wind around the Earth where all those nasty particles may or may not go around and keep flowing back into interplanetary space. So this is called the tail. Now just notice, of course, that these magnetic lines go around like this into the North Pole and the South Pole. And that causes some interesting effects. In other words, it's kind of a weakness in the shield because it's not, the North and South Pole aren't shielded magnetically. It's where the lines emanate or terminate. So much of the charge goes past us, but it does leak in, can go in to these cusps at the North and South Pole. Yes?
If anybody would still be using a compass, would that change the compass reading? Maybe?
I believe it does. It can. I mean, it doesn't permanently change the Earth's magnetic field, but it can influence it. I'm pretty sure I've read where people have noticed their compasses deviating under severe storm conditions. Yeah. Anyhow, when we have things like the coronal mass ejections, which is one of these things here that's blown off the surface of the sun, in it has a magnetic field. It's captured part of the sun's magnetic field in there. It's not just hot particles, ionized particles. There's part of the sun's magnetic field in there. It's a structure into its own self. And of course, it's flying off into space, maybe towards us, maybe not. So the thing is that if you have, let's say the Earth's magnetic fields are like, this is north up here, right? And you have this lump flying towards Earth with its embedded magnetic field. And its magnetic field is the same way. So it's coming like this towards Earth. Well, north and north, like magnets, repel. Okay? Like poles repel. So that mess of stuff will be repelled and go around Earth into the tail. On the other hand, if the magnetic field that's embedded in this is oppositely pointing, you've got like poles, and so they couple, and all the stuff that's in that cloud will then follow the magnetic lines into the north and south polar regions. You might remember last week we talked about those, well, these prominences here. This is a magnetic field that's come out of the sun. It's captured the hot plasma because the plasma is charged particles, and a magnetic line will capture the particles. They spiral around the magnetic line. And that's what you actually see is the hot particles that are captured by the magnetic field. And that's what happens in that case where the magnetic fields couple and those particles are captured by the Earth's field, but they don't go past, they go in at the poles. so we don't exactly escape. That's what you get. That's why we have auroras, which is kind of neat. All those highly energetic particles that end up into the polar regions, of course, are ionizing the upper atmosphere there intensively, causing more ionization, which results in visible light. When the recombination, it's not the ionization that causes the auroral light, it's the recombination when the electrons fall back down to their original atoms, releasing energy, which is in the form of light. Anyways, so these precipitations at the north and south poles are the auroras. And if you have a path, an HF path, that's going over a polar region, either the north or the south, you're going to get a whole pile of funny effects when these auroras are running. They give a sort of like a drain pipe sound, like someone's talking through a pipe. This is because you're getting path fluctuations, phase shifting, because the paths are all slightly different, even though it's just in your one signal. You get all sorts of rain barreling sounds, and you say, oh, it's got to be a polar path, or worse. Back in cycle 19, I think the 1958 peak, I saw this sort of thing in Victoria. It was amazing. It's just roaring like crazy. And on my old Heathkit 10-meter transmitter, I worked people off the aurora. In other words, the signal was being reflected from the aurora. And it had a very characteristic raspy sound to it. It wasn't very high fidelity, but it was just amazing that you could do that. I haven't done that since. Things have not gone uphill since 1959. They've gone downhill. Okay. So, the geomagnetic storm. Disturbances to the magnetosphere because of particle charges being captured by the magnetic fields that are carried by the solar wind. Solar wind is the most common purveyor of disturbances because the solar wind is relatively constant, but it can vary significantly when there's activity on the sun. And this is what drives the aurora phenomena. These geomagnetic events, they are called that because they affect the Earth's magnetic field. What's happening, I think it's in a further slide, but I'll explain it now. You know, up there in the E and F layer, you've got these electrified layers continuously. You know, they're not just this layer here and that layer there. It's a continuous ionization, more and less. But it is full of electrons. And electrons can move, like current in a wire. And they do. And they're called electrojets. These currents that flow in the ionosphere are fueled by the solar wind, the Earth's magnetic field. It's a complex relationship which I can't quite figure out. But the electrojets flow. So if you think of it as current flowing through a wire, it creates its own magnetic field, which interacts with the Earth's magnetic field. Now, the Earth's magnetic field is way, way stronger than the electrojet magnetic field, but it's sufficient that you can measure the difference. And there are magnetic field monitors all over the surface of the Earth, just looking to see how much the Earth's magnetic field is twitching and tweaking. And the amount that is happening is an indication of disturbance in the ionosphere. In other words, it's not just a nice, steady, everyday current. It's probably getting bounced around by these flares and storms and things, showing that it's highly variable. Maybe it's increasing, maybe it's decreasing, but it's another symptom of a disturbed ionosphere, which again affects propagation. So that's why it's called a geomagnetic, because it interferes with the Earth's magnetic field. Changes it slightly. I mean, it changes it in terms of nanoteslas, which is a very small amount, but it's detectable. And it acts as a good indicator. Now, we're not going to go through having to memorize this for the exam at the end of the night here. But these storm ratings are characterized. We'll see some other examples where you say, okay, there's a geomagnetic storm happening, we're told. It's designated by the letter G. It could be a G1 level storm with minor fades, some auroras, all the way up to G5, which is extreme, where auroras reach down into the south of the US instead of just the north of Canada. And in terms of our propagation, there probably isn't any. So you'll see later on that we do refer to these things, or the reports, the solar indices that we were going to see will say there's a G2 storm warning. So, you know, G2, oh yeah, it's got to be a geomagnetic. Well, it's only moderate and only seems to affect Canada as usual. Radio blackouts. That's when you lose propagation, like it's just not going to propagate anywhere. It's caused by high energy X-rays, basically illuminating the sunlit side. You're not going to see it on the dark side. The X-rays are produced by those flares. We know when we see those great prominences go up. And then there's an explosion as energy is suddenly released for whatever reason. Produces large amounts of X-rays. They penetrate pretty deep into the ionosphere because they're so energetic. And the absorption that's resulting from that penetration, is very significant. Again, storm ratings are 1 to 5. If it's a minor storm, maybe some blackouts on the sunlit side. If it's an R5, you might lose it for a long time. Over here is a rating of the intensity of the X-rays. We'll see a graph on that later, but M1s occur frequently, M5s, you see those these days. Every once in a while an X1, by the way, this is 10 times worse, that's 10 times worse than that, that's 10 times worse than that, you know. So it's a factor of 10 in each one of these ratings. You have an X1 flare, which has happened a few times in the last year or so. It's very noticeable. You can be, I noticed it on the contest mostly. You know, you're contesting, making lots of contacts. The band is full, all sorts of contacts all around, just everywhere. You can't find a clear frequency, it's so good. And then suddenly it's like everyone gone home. Where did everyone go? You know, you start calling CQ, nobody answers. There's a signal here and a signal there, work them. That's what's happening. You've had a blackout, the bands just go dead. And it's not hard to tell. So an hour or two later, things kind of get back to where they were, maybe. So you're going to lose an hour, hour and a half of valuable contesting time. We're not happy about that. Right, Keith? Right, Dave? Okay. And then there's the solar radiation storm, which is high energy protons penetrating the polar regions down to the D layer, increasing RF absorption. As I've mentioned before, we get loss of paths over the polar regions. And depending on the intensity of this, you know, the auroras, and by the way, the auroras at the North Pole and the South Pole are what they call conjugate. It means the shape of the aurora at the North Pole is exactly the same as the aurora at the South Pole, because the magnetic field funnels apparently the equal amounts of energy in the same pattern into the two different polar regions. And if you look at them, and we'll see how you can see that, there, sure enough, there's the aurora around the North Pole, and you look at the South Pole, and there it is, just looking much the same. Kind of interesting. Anyways, as the intensity of the radiation increases, the aurora moves in the northern hemisphere further south and further south. So the ionization is getting more and more intense at lower latitudes. And again, the letter S, minor storms, extreme storms. Be nice to see a 4 or 5 here, and we probably get a good auroral display in Vancouver if it ever stops raining. Let's see if this works. Okay, this is a website I use. It's very popular. It gives a whole pile of parameters on the state of the ionosphere. Now, you don't know what a lot of these things mean right now. I'm just going to scroll through it, and you can see there's all sorts of tables, charts, numbers. I'm going to explain them to you. There you go. There's the North Polar. That's a nice map there. You can see the aurora circle there, and there's the aurora circle over the South Pole. That's real time. That's what's going on right now. This is a real-time web page. What else have we got here? Oh yeah, this is the X-ray flux. The X-rays coming down to Earth. You can see these spikes. There's a spike, there's a spike. These are small flares. They're not very intense. The scale here goes A, B. You know, this is hardly noticeable, just noticeable. Getting noticeable. That's concerning. That's a monster. So you can watch this in real time. You can just dial this up. And I use this graph too when I'm contesting because I want to know what's going on. And I'm watching for these bursts. And if I see one of these bursts come along, I notice that it correlates exactly with everybody going home. They haven't gone home. You just can't hear them. Oops, don't want to do that. This is a gray line, which is also quite useful. It hasn't got a lot. Well, it does have something to do with propagation. This is where it's dark right now. And of course, this is where it's daylight. Along this terminator, around the world, you get sometimes very extraordinary propagation. Because what's happened here is that it's not nighttime, it's not daytime, you're in between. The D-layer ionization has pretty much gone away, which is good. Absorption is going down rapidly, if not gone. But the E and F layers are still quite highly ionized. And that occurs all along this perimeter. Which means if you, this isn't very good, but if you happen to be on this perimeter, let's just say Vancouver was here, you would find you probably got a really good path into this part of the world, you know, the Middle East. And that's what you would be listening for. And sometimes it's amazing. It's just like a pipeline. You know, I've worked guys in India when we're on the terminator, just because the terminator there goes along here, down around the South Pole, back up over to India, and there they are. So just keep that gray line in the back of your head there. This one is a MUF map, maximum usable frequency map of the ionosphere in real time. Kind of hard to see, but on here you'll see numbers 37, 35. These are the maximum usable frequency contours, which are reflecting the degree of ionization all around the world. These green lines are the aurora circle, which means you'd rather not have a path through there or down here. This is the gray line through here. And so we could say that, let's just see, each one of these is about a megahertz. 10. So over Canada, the maximum usable frequency is about 10 megahertz. So right around here above us, it's about 11 megahertz, which means that the higher frequency bands are going to be closed because there's not much above 10 megahertz that you're going to hear. But you also have to keep in your mind that your signal is propagating out here somewhere. If you're looking for say a long hop over to Asia or Australia. So your signal doesn't hit the ionosphere until somewhere out here where the MUF will be higher. So it's not quite as bad as it looks. Just keep that in mind. Pictures of the sun, which you saw last week. We saw what the sun looks like, how disturbed it is, the sunspots. We can see the prominences, the loops. These are the magnetic loops.
Is that real time?
That is real time.
All the time?
All the time, real time. Yeah, it's amazing, eh?
Yeah.
Yeah. So go look at that just for fun. I'm going to close that. Okay. So we have these on the stations. I have them at home. Other folks use it. Other folks use different sites. But, you know, I've sort of bombarded you with all these parameters. So what are they? Well, there's a lot of them. This one, the solar flux index, SFI, we talk about that a lot. We say, oh, what's the solar flux today? Oh, it's 110 or something. Some people prefer to use the sunspot number, which is when some poor bloke somewhere, or a lot of them, try to count the number of sunspots on the surface of the sun. They have a methodology, and the correlation between these two is quite good. But I prefer this one because it's a direct measurement of the solar flux. We talk about the A and the K index a lot, and I'll tell you what those are all about, but those are the magneto indices that tell us how the Earth's magnetic field is doing, which in turn is telling us how the ionosphere is, whether it's disturbed or it's quiet. The solar wind, what's it up to? What's the X-rays up to? What are the protons doing? Is there any auroral activity? It's nice to look at, but it's not good for propagation. We kind of looked at the auroras, and we looked at the MUF maps, and we looked at the solar images already. So solar flux index is right at the top because it's really important, the SFI. It's measuring the RF energy being radiated from the sun at 2800 megahertz. It turns out that that frequency provides a very good correlation to the intensity of the ultraviolet radiation. But we can receive the 2800 megahertz on the surface of the Earth. It's a little more difficult to tell what's going on, 500 or 600 kilometers up there in terms of the ultraviolet intensity, but in these days of satellites, that's also measured. But this is basically the easiest index to understand in terms of how much energy the sun is pumping into the ionosphere. It correlates very well with the level of UV, and it's the higher the solar flux, the better the MUFs, the higher the MUFs. This, by the way, is the Solar Flux Observatory at Penticton. It's one of the few in the world that measures solar flux, and it's generally the one that's taken, at least by North Americans, to be what the solar flux is. Interesting place. So it's an overall guide to the ionization levels. If you see a solar flux of, let's have a look here, 164, that's nice. That's good. If you see a solar flux of 52, turn the radio off, I guess. But it has these other things on here. A equals 1, that's the A index, that's the K index. What do they mean? Oh, before we answer that question, sunspot number, yeah. Since we have the solar flux, so we can also count sunspots somehow on that. I don't know how. But this is the graph of sunspots versus the solar flux. It's a scatter plot, and this is the average value, but the sunspot numbers and the solar flux correlate quite well. And that's been known for decades and decades, except lately. At the Orca DX convention there in July, our Penticton solar astronomer came down and said, things aren't quite what they used to be. He says, we're a bit worried. We thought we knew what was going on with the sun, but actually I don't think we do, because he showed us this graph and he said, this no longer works. There's a difference between the solar flux radiation and the sunspot numbers. They're not correlated anymore. And he showed us the plots. And it looks like this, and then all of a sudden there's a line that goes way off the side, and another one that goes way off the side, and another one that goes way off the side. In other words, the sunspot solar flux correlation is doing something that has not been seen before. And there's no known answer for that. We all kind of go, oh, just what we wanted to hear. Well, the last 3 solar cycles have been going like this. Each one is less than the previous one. And it may be an indication that things are changing within the sun and that the lack of correlation is being made apparent. But nobody knows. It just wasn't great news. Here's the solar wind. It's got little gauges. You can look up these gauges. Yeah, it's pretty neat, eh? And they'll move. So this is the magnetic field in that in the solar wind. Like I said, if it's like this, or like, well, if it's like this, green meaning it's north to north, it means don't have to worry about it. If it's in the middle like that, there's probably a component that's perpendicular. And if it's down in the red, it means it's this type of thing. So if you see the magnetic field component going into the yellow and red, that means things aren't good. This is the speed. This is how fast the solar wind is approaching us. This is quite low, 300 kilometers per second, not per hour. And it can vary by, quite a factor. This dynamic pressure is, I don't know what to do with that, but it's, when the solar wind is blowing against the magnetic field, it's pushing it in, as you saw, it distorted the magnetic field. And that's what they relate to the dynamic pressure, which sort of gives a measure of the compression of the Earth's magnetic field. So if these things are all up in the red, time to get the lead suit on, I think.
Yeah, at what point does it get dangerous?
I don't think it does, no.
No.
But you know what I mean. It's kind of neat. The A and the K index, now these are often used, just like the solar flux. I guess solar flux is one of the biggest ones we talk about. The A index and the K index are the other ones we talk about. The rest was sort of background information. And I said it's geomagnetic indicators. I mentioned that the ionospheric layers have electric currents flowing in them, going around. I don't know, I think electrons are injected into the electrojets, and they on the sunlit side, and they may flow out into the tail on the dark side. I don't know, Nick, do you know about that? No, neither do I. I tried reading about it and I'm totally confused. But there's no question, there's lots of electrons up there, and they are moving, and they do infect the magnetic field. So changes in the electrojets are due to the solar wind disturbances, basically injecting particles into the ionosphere. And the A and the K measure the degree to which that's happening. Oh yeah, okay. So again, the A index and the K index, which are measuring changes in the Earth's magnetic field intensity. That's what they're doing. They're measuring the small changes to the Earth's magnetic field. And the A index is, well, and the K, they're both measured every 3 hours worldwide. The A index is an average over a 24-hour period. So they take 8 measurements during the day, average it, and we'll say that the A index is 5. The next 3 hours, they'll drop the oldest information off and attach the newest one, so the average is a little different. So the A index is an average over 24 hours. The K index is also a 3-hour reading, but it's reported every 3 hours. So you might have a history of the A index saying, the Earth's magnetic field is quiet, there's not much disturbance going on, the ionosphere isn't going to be ratted up. But you see the K index is high, which means something's changing now. Okay, it's not reflected in the A because it's a long-term average, and the K is sort of, well, not your instantaneous, but your short-term measurement. So you'll see K values that are headed upwards, which may be within a day are followed by A levels starting to rise as well. So one's a smoothed measurement, the other is a more instantaneous measurement. And this is the table that relates these things. So we look for A indexes that are down in this region as being normal. If it's up here, we're in trouble. And the K index sort of correlates with these in this fashion. And these are the descriptions. Just so you know, the Earth's magnetic field is about 60,000 to 26,000 nanoteslas. I'm sure you wanted to know that. But there it is.
I have a question.
Yes, question.
When I was a kid in southern Manitoba, I was out with my bike
Yes.
at night,
Yeah.
pitch black,
Yes.
no lights, no car, no moon,
Yes.
nothing. And there was an incredible display of what we call northern lights.
Yes.
Just totally beautiful.
Yes.
And I was standing there and suddenly realized I was hearing them. What was I hearing?
I've had the same experience. And people deny that you can hear. Yeah, the question is, Bob here could hear the northern lights. And I agree with you. I think I've heard them too. In that Victoria display that I mentioned earlier.
Well, how old were you?
3? No.
No, were you 25 or younger?
I was about 18.
Yeah, because your hearing dissipates as you get older.
Oh, I know that.
What are your hearing aids?
I heard them when I was young.
Yeah.
My frequency response was, and I'm sure Bob's was better then than it is today.
I think so, yeah.
Yeah, okay. So we'll allow that. Yeah, there's no known mechanism for hearing audible emissions from the northern lights. So science says, no, you can't possibly hear them because there's no way. But I've heard them, Bob's heard them. So take our word for it that under perhaps displays of a great magnitude. I mean, they are absolutely splendid and intense and
Yeah.
just moving all over the sky. Unbelievable. Yeah. Yeah. So, you and I concur. All right. So, if we have an A of 0 and a K of 0, the ionosphere is perfect. If we have an A of 25 and a K of 3, I'd say we're looking for trouble. If you had an A of 50 and a K of 5, things are becoming difficult. So things will be unstable, propagation unpredictable, and probably a bad day, go do something else. Now here's the X-ray flux, which I've talked about a little earlier. The flares produce the X-rays, and they're measured continuously by satellites. You can see that there's this GOES 15 and GOES. Yeah, these are two satellites, or maybe it's the same satellite, but are measuring at two different bands for spectral energy. So this is measuring at 4 angstroms. This is measuring at about 1 to 3 angstroms. Yeah. So anyways, two different levels. It doesn't matter. They correlate the same. And this is what you look for. Now here's one that's peaked into the M1 region, which means it's something to pay attention to and might be noticeable on the bands if you were active. So these things are what you call the sudden ionospheric disturbances, because they just happen like that. It's not predictable. It just shows up. The X-ray classification, same thing. Class A, B, C, M class, X class, X class, X class. Each one going up by an order of magnitude. Watts per square meter doesn't sound like a whole lot, but when you're talking about millions of square meters up there, it's a lot of energy. Seriously disturbs the ionosphere. And so you look at this and they'll say, oh, there's a class B flare. You don't pay any attention to that. If you see a class M, you'd say, that's interesting. And a class X, you'd say, we're looking at possible problems. The energetic protons, it's really in protons per cubic centimeter. If you have a deluge of protons suddenly arriving in the solar wind, they find their way into the polar regions, and they just obliterate the ionosphere up there, and you get what's called a polar cap absorption. In other words, any propagation that you expect to get over the poles, north or south, is gone until that dissipates. There's the auroral activity. That display is very much better now than what it used to be. It was okay, but that one's a really nice high-resolution display. So, if you wanted to go north and look at the aurora, you could look at this map and say, well, better to go somewhere over here in the world rather than the Yukon. It does take time to get there. Yeah. So you see it there today and it's not there tomorrow. That's the problem, yes. Anyways, that's the auroras, which is kind of neat. There's the MUF maps, which we talked about, which give you an idea of what the maximum usable frequencies are worldwide in real time.
Is that on the website that you...
Yes, it is. Yes. All this is taken from that website.
It was listed on there at some point.
Oh, yeah, it was. Yeah. Remember when I went to the web there and we scrolled down the... Yeah, it's all taken from there.
Okay.
Yeah. So it's all in one place, which is really nice. But there are other places where the same information is conveyed. I just happen to like this one.
What's it called?
QSL.net/propagation, I think.
Okay.
Yeah, that's one source. That is where it's coming from. It's coming from a commercial source.
Oh, yeah. Yeah. It's just that this particular web site puts it all together, what I like. But, I mean, Keith has his favorite, and I don't know where Dave goes for his.
Well, actually, I look at that one every morning.
Oh, well, there you go. So if it's good enough for the president, it's good enough for you guys. So this was just an example. Solar flux is good, 164. A index is 1, pretty good. K index is 0, couldn't ask for much better, actually. Geomagnetic field would be quiet, says so. Radio blackouts, a minor warning, minor blackouts. There was an M-class flare, the X-rays came down, and there's some absorption. Observation, 20 meters was dead, even with this good report. 10 meters was open. You think, oh, that's interesting. Well, The ionization was obviously, as I said in one of my earlier mentions, that over-ionization is okay to a point until it becomes absorptive. But if it boosts the ionization, yeah, you'll get absorption at the lower frequencies, which is the longer wavelengths, but the higher frequencies may come alive, which is what happened here. 10 meters was open, 20 meters was dead. The lower frequencies were absorbed, but the solar flux at 164 gave us a high frequency opening. And here's the flare that happened that caused all this to, and you can see it lasts for a while. It's not over instantly. It might happen darn near instantly, but the better part of the day is wrecked by some of these events. And from all these indices, they do forecasts on the same page, Bob. They do the forecast there. Then they'll say space weather for the next 24 hours is predicted to be minor, blackouts reaching R1, don't worry. Solar flare, M class, geomagnetic field is mostly quiet. So this is how they're talking about the space weather. Things are quiet or stormy or whatever. But that's what it's all about. The satellites are looking at a lot of things these days that they weren't when I was starting out. There weren't any satellites then, come to think of it. So that's basically it. These are some references that you might want to go look at. That other one, Bob, that link you were wanting is further back in the slides. So this will be posted and you can go click on it and see it, yeah. I repeated it in number 3. This one? Try it. No. Yeah, this is a different appendage which just gives you some sort of data. You can see same sort of thing. It's looking at, there's the South Pole, images of the sun, maximum usable frequencies, X-ray absorption, and so on and so forth. I mean, you can go on. This is endless stuff. The amount of data is overwhelming. It's pretty pretty interesting that there's this much stuff out there. Maybe I can play this one. Just hang on for a second. I thought this was pretty fabulous. This is an application, I'm not sure who wrote it, Keith?
It's a commercial product, I believe. This is a demo for it.
Yeah, and what this is showing is the real-time activity in the E and F layers. It's measuring how it's changing with time. And it's plotting it. I'm just going to get past the... What they did is they took the CHU time signal, which is Canada's WWV, on a frequency of 3330 kilohertz. And he's done this in the evening. The path is in darkness. And he's looking at the spectrum. Notice he's only looking at 5 hertz wide. I mean, very narrow look at the spectrum. He's not looking at a whole pile of frequency. This is the CHU signal, the time signal. And it's changing in frequency because it's measuring the Doppler shift of the ionosphere as it moves up and down or becomes more or less ionized in real time. And it's plotting it over a bandwidth of 2.5 to minus 2.5 hertz. So you can measure the height. You could measure the height because you know how long it takes to go up and come down again, but that's not what this is doing. This is measuring the Doppler shift. This is the place at which you would say refraction is taking place. Yeah. There's an interesting first hop, double hop. In other words, it's coming by 2 different paths. The long one, first hop, or a second one off the E layer probably, which is 2 hops, because it's lower down. So I'll let you, play with it. You can look at the whole thing, but I thought, if you want a visual representation of what's going on, that's a hard one to beat. Yeah, that's pretty neat.
He used the word reflection on there. Did he really mean refraction?
Well, like I say, there's a lot of liberty taken with.
Okay.
It is a refractive. It has to be a refractive
Yeah.
process. It
Yeah,
can't be a
right,
reflected
right.
process because of the.
Well, the second hop would have one reflection.
Yes, it has a reflection.
Yeah.
Yeah. So there's a refraction off the surface,
Yeah.
reflection, refraction, and then you get it again. Yeah.
Well, but if it's 90 degrees going up, it will reflect right down, so.
It would refract right down.
You think so?
Well, yes, it has to. There's no reflective surface. It's totally refractive to go up, and if the gradient is sufficient at that frequency, it'll turn it 180 degrees. But there's no reflection. There's no hard surface. It just doesn't work that way.
Well, so in the 50s or in the 60s, when you want to find out what the solar flux is, where would you get information from?
Probably nowhere. Not that I know of. I wasn't that astute at the time to worry about it. My receiver in those days was so deaf it couldn't hear anything worthwhile anyways. But today, technology and antennas and all the other stuff is vastly
She
improved.
started with that prior to Penticton, which I think was just after the war, wasn't it?
It could be, yeah. I'm not saying it wasn't available, I just didn't know about it. Any other questions? Okay, thanks very much.
Thank you, John, and I'd also like to thank Colton and Adam for doing the video work. I mean, as you can see, there's a fair bit of stuff has to get humped around
Yeah.
for that, and once it's all sorted out, we'll put the links into contact for you.
Yep, very good, thanks Keith.